Classical Physics Tutoring, Chapter 3, Section 3, Sound Wave. Now, so far we talk about transverse wave, which is like a water surface move like that in the ocean, the ripple. Those are transverse wave. What it is the movement is orthogonal to the direction of the wave movement. This wave movement is animated wave movement. Okay, so that's transverse wave. Now, in this section, we consider sound wave. Sound wave is longitudinal wave. The wave direction and oscillation is in the same direction, so the air pressure oscillate this way and sounds propagate this way, so they are same direction. That's a longitudinal wave. Okay, now later you see the wave equation. Basically, if this is x, it goes double integral n square x and 0 kind of equation, and this n indicate actually speed, so the speed square equals lambda RT over m, and this we can make an equation of the pressure by time, and local pressure move, expand, shrink, and that's the speed we will get. And we know the Bill is constant, the R gas constant, absolute temperature, m gram molecule. We enter that, then sound speed is typically this T is the temperature from 0. So say about 20 degree, it's going to be 12, so it's going to be 343 meter per second, and that's we call Mach 1. In English we say Mach, but in German's original word it's a Mach 1. It's Mach 1, and that's a sound speed. And what happened is we talk about this in the Doppler effect in the previous video. When it's come to the sound speed, this point, the source of the sounds moving at the same speed as the sound's speed, then it's going to cause shock wave. And shock wave is not the wave expressed by this equation, so shock wave speed doesn't follow this equation. Okay, and shock wave is simply just pressure shock moving forward, and totally different equation for this speed. It's not sound speed anymore. Okay, we talk about this in the previous videos. You can go back and review the video, Doppler effect. And when it's exceed Mach 1, then shockwave become even strange shape, because the source is moving faster than the sound speed, so it's kind of a reverse wave kind of things. This kind of equation cannot explain this speed. Okay, so this is a new physics, because we don't have many things that exceed the Mach 1, and the fighter jet typically go Mach 1 to 2 maximum. The hardly go over 2. Okay, so now the sound wave actually can go either way, transverse or longitudinal. See, if you have a solid material and you vibrate this, then that wave propagate this way. So this is the transverse, and this material, if you hit this way, then this pressure makes a sound internally in the solid material, and that's a longitudinal wave. So the sound wave inside the material, solid material, can be either transverse or longitudinal. Okay, and this transverse is possible because it has the force between molecules, so it's moved like the rope whipping. Okay, so this is exactly what earthquake is. So we talk about earthquake a little bit here. So earthquake is a kind of sound wave, and it's just a low frequency, so you cannot hear the sound for human, but maybe elephant can hear the sound. The sound is coming, so they can hear the earthquake, but human cannot hear. It's only feel the vibration. And there are two waves in the earthquake component, longitudinal and transverse, and their speed is different. So here it is. It's so-called P wave and S wave. Okay, and I believe P wave is transverse and S wave is longitudinal, is slower, so there is a time difference. And using this T, we can determine the epicenter, the distance to the epicenter, because if distance is L and P wave speed is Vp and this is Vs, right? Okay, and difference time T. So L Vp is faster plus T is going to be L Vs. So if we know the T and Vs Vp, the typical speed of the earthquake, then we can find out L, and that's the way we know by measuring the earth shaking equipment like this. The this mass has inertia, doesn't move that quick, and this needle moves, and this is rotating paper, and needle has ink, so it's record the paper this movement, and putting the equipment in the 2 different directions or 3 different directions, we can measure the oscillation on each direction, put them together, we can find out the T. And once we know the T, we know the speed, typical speed on the ground, so we find the distance L. Now we need 3 such a data to determine epicenter. The reason is the epicenter typically deep in the ground, so we know the distance S, but actually epicenter is the deep down, the distance D from the surface. So when you take a 2, R1 and R2 using this equation, it has a 2 intersecting point. You need one more. Then we have a 2 intersecting point for this. So we draw the line here and draw the line here. We know the epicenter is here below. Now we measure the distance from here to here, and surface distance we can determine the depth d. So this is the geometry equation. You have a triangle and you S1, S2, right? So that's the surface distance, you know. Okay, so find the D. Okay, so that's the way they determine the depth of epicenter. And this is like a sound wave. Exactly from physics viewpoint, earthquake is a sound wave. Okay, so sound equation. Now when something vibrating in a music instrument, okay, it's a fair assumption that this wave equation is the multiplication of field equation and time dependent equation, because there is always a fixed point in the music instrument. Vibrate, there is always a fixed point. So this is the good assumption to take. Okay, and the wave equation we have typically is this one, right? So we take a derivatives on t twice and x twice, then this become like b square f equals g double prime, okay, this way. And that means this must be a constant, because two different function, you take a derivative, take a ratio, and they are equal. That means somehow this is a constant. So from this we can get fw x plus n square 0 and g double w derivatives b square gt equals 0. So we get two independent equation, and this is assuming that the musical instrument is behaving this way. Okay, so remaining is just solving this equation. Okay, so you know the equation dfx dx square plus n square fx. This equation's solution is nx plus theta, right? Okay, so but depend on the music instrument. It's like a flute. The one side closed, other side is open, so it's probably oscillate this way or this way. This is a half, this is 1 plus 1 half, and so on. So the string, both sides are fixed, so it's going to oscillate like this or like this, right? Or like this. So this is n equals 1, n equals 2, n equals 3. So music instrument provide a boundary condition. This is called a boundary condition. For the differential equation. And string is like this. Xylophone, if both are open, then it can be like this, the way the frequency oscillate, or like this, or only one side is fixed, it can be oscillate like that or like that. Its boundary condition is different depending on the music instrument, and the type of string is going to determine the waveform. But this frequency is determined by the boundary condition. Okay, so the flute, if you make a hole here, you open the hole, then suddenly it's oscillate like this. So it's going to change the frequency. So depend on, oh, it's outside. You make a hole on the flute. The flute is change suddenly frequency by opening the hole here. Okay, because the sound boundary condition change. And the string, like a guitar, you sometimes you put the finger here, then suddenly frequency change. Okay, so this n is called eigenvalue. And you have many possible solutions to this differential equation. And many different equation solution given by eigenvalue. Eigenvalue can be the 1, 0, 1, 2, 3, or depend on music instrument, half, 1 plus half, 2 plus half, so on so. So they are all solution to the differential equation. Okay, and this differential equation, if you compose with a characteristic of air, gas, then you get this sound speed equation. Air, gas, temperature, ground molecules, gas constant. Okay, so and so. So that's, we can analyze all the sounds using this differential equation. Now, music and the frequency, how the music frequency is assigned. So this is interesting. Computer assign every music note the number. It's called MIDI. MIDI number, okay? And start with 12 all the way, increment by 1. But frequency is not increment by 1, it's going to be increment by the exponent function. And for example, lowest note C on a standard piano is 32.7 Hertz, and the human ear cannot hear this, it's too low. And lowest note for cello, the lowest note for viola, the middle C is 261.63 Hertz. So that's a middle C, note C frequency. Okay, this is Do for Do Re Mi, right? And sounds increase, the frequency increase by exponent function, but human ear, at the input stage of a human ear, has a log function. So the sound frequency increased by exponent function. Because of log function, human feel this frequency increase. It's a double every note. Feel like linear increase. Okay, so for example, this is a human ear, and healthy ear feel all the frequency at the same level until over 2000, then it's start having a hard time hearing it. The 8000 is almost impossible. The dog go all the way like this. Dog can hear the higher frequency, way above, and lower frequency is like this, 50. Human cannot hear much, but elephant go all the way here. Okay, so each animal has a different range, but they all has the same characteristic, has the log function on the ear. So frequency increase double like exponent function. The human feel is just linearly increasing. Okay, and the aging effect of ear is typically like, overall hearing deteriorate, but this key frequency relatively remains same and drop higher frequency faster. Okay, that kind of human ear. And we talk about middle C, the human voice is somewhere around 500 hertz to some female high tone voice is 1000, right? And let's see, highest note 2217 hertz on the piano, and this is probably the highest tone human can hear, right? And actually piano can go 4186. That's too high. The human ear hardly can hear this. So piano cover very wide range for human ear. It's not wide enough for the dog, but for human ear it's pretty wide enough to cover entire audible range. So human ear has a logarithmic function, and sounds, the sound wave form and frequency is two different things. And the waveform is a characteristic of sounds, like guitar sound, piano sound, each waveform different. So how do we change this waveform around? We have a very good math analysis, and that can convert domain, time domain. This waveform is time domain we're talking about. This is the time, right? We can convert into frequency domain. The frequency domain tells you what kind of component of frequency included in this, the wave. So when you hear the guitar, computer capture it and convert into frequency domain, then computer can tell which note is played and what is other notes are overlapping to create guitar sounds. Okay, and I made another video for this free Fourier analysis, so I don't repeat it here. you should watch that video to understand Fourier analysis. So the great things about this frequency domain is one of the application is like the recording machine used to have a high frequency noise. So suppose this is the perfect sound, then noise, there's this much noise on the high frequency. So the before recording, this is recovered sounds. Before recording, they suppressed, they emphasize this part, this range only. Those sounds skewed, right, and recorded. Then when they recover, they suppress this to recover the original sounds. So the noise relatively become very tiny, and this is a Dolby function. So this was a patent the company Dolby founded with this basic patent, and all the recording machine had a Dolby function before. That means the higher frequency component by Fourier analysis is emphasized before recording, and when you replay, they suppress all the noise together and recover the original sound. So it's almost like sounds disappear magically, the noise disappear magically. Okay, that's a kind of application they use Fourier analysis. Okay, so Fourier analysis is actually used in many places, like the image compression and the sound compression, then compression technology. So what's happened is, instead of recording all of this information on a time domain, you convert it into the frequency domain, and you record the frequency domain, which is much smaller amount of information, right? And when you decompress, you recreate frequency domain to the time domain, but image it's going to be x, y, the dimension domain to the frequency domain, and they convert frequency domain back. Frequency domain is much less information, and so it's like a JPEG compression is using this technique. They decompress using Fourier series, this recovering original XY information dot. Then you have image come back, and you lose a little bit of information. The reason is this frequency domain go infinite amount, and a very tiny amount existing here, but computer cannot handle, so they truncate and recover from remaining. So you lose some amount of accuracy, but the compression rate is very good using the Fourier series. So that's a kind of application beside the Dolby. So there are many things they can do at the frequency domain. Okay, so that's all about the sounds. I hope you enjoyed this video, and if you like, subscribe.